Okay, so let's talk about this invisible shield around Earth. It's something
hmm
we don't see, but it's absolutely crucial, right? Earth's magnetic field. We're doing a deep dive today into why it's so important, especially now with all our technology.
Exactly. Its main job, its vital role, is creating the magnetosphere. You can sort of picture it like a planetary bodyguard.
A bodyguard? I like that.
Yeah, it deflects dangerous cosmic rays and also the solar wind, that constant stream of particles blowing off the sun. Without it, we'd be bombarded. Life would be, well, it'd face a huge challenge from space radiation.
And the really wild part, which maybe feels a little bit, I don't know, concerning, is that the shield isn't fixed. It's not static.
Not at all.
The sources we looked at really emphasize how dynamic it is. It changes. Sometimes, apparently, quite dramatically over long periods. They mention evidence of polarity reversals.
Yeah. Complete flips where magnetic north becomes south and vice versa. It's happened many times in Earth history over geological timescales. It's a
Yeah.
natural thing the planet does.
Okay, so it's natural. But the big question the sources seem to be asking is, how does this changing force, this planetary dynamic, interact with us, with our civilization that's, completely built on tech, satellites, power grids?
That's the core issue. How does this fundamental planetary process mesh, or maybe conflict, with our modern, technologically dependent world?
Right. So that's our mission for this deep dive then. We're going to unpack the research you brought, try to understand where the field is now, look at how our tech is vulnerable, and see what researchers and agencies around the world are doing. So by the end, you should have a really solid handle on it all.
Sounds good. Let's start at the source. Where does this field even come from? The material points deep inside the planet, to the core.
The Earth's core.
Specifically, the liquid outer core. It's superheated, swirling liquid iron, essentially. This motion generates the magnetic field. Think of it as a giant natural dynamo.
A churning dynamo, which explains why it's not static, I guess. It's always moving, always changing.
Precisely. And the sources highlight some specific changes happening right now that scientists are watching very closely. The first big one is the field weakening.
Weakening how much?
Well, measurements over the last, say, 150 years or so show roughly an 8% decrease in the main dipole part of the field's strength.
Okay, 8%. Is that a lot? Should we be worried?
Well, the sources are careful here. They say that geologically speaking, looking back millions of years, this rate isn't necessarily abnormal, but the key thing is we can measure it now with such precision. So it's definitely something scientists are tracking closely to see where it's headed.
Okay, so the overall strength is dipping a bit. And what else? You mentioned other changes.
Yeah, another fascinating one is the movement of the magnetic poles themselves. They aren't fixed points.
They wander around.
They do. And the North Magnetic Pole in particular has been moving pretty fast recently, accelerating towards Siberia, although the very latest data suggests it might have slowed down just a tiny bit.
Towards Siberia.
Ah.
Okay. Does that actually affect anything practical? Like, does my compass still work?
Well, your pocket compass is probably fine for hiking, but for serious navigation, yes, it matters. That pole drift means the world magnetic model needs more frequent updates.
What's the world magnetic model?
It's basically the standard map of the Earth's magnetic field. It's used for everything from, ship and aircraft navigation to directional drilling for oil and gas. If the map is wrong because the pole moved, your navigation could be off.
Gotcha. So more frequent updates needed. Okay, weakening field, moving pole. What else? You mentioned something called the SAA.
Yes, the South Atlantic anomaly. This is a really interesting one. The sources describe it as a huge area, mostly over South America and the South Atlantic Ocean, where the magnetic field is significantly weaker than average.
Weaker, like a dip.
Exactly. You can think of it as a big dent or maybe a soft spot in our magnetic shield.
What happens in this dent?
Well, because the field is weaker there, charged particles from space, the ones the magnetosphere usually deflects, can dip much closer to the Earth's surface.
Okay, and that's bad
For satellites, mainly. The research is clear on this. When satellites fly through the SAA, they get hit with a lot more radiation.
Right.
The sources mention things like the International Space Station, the Hubble Space Telescope. They often have to take precautions. Sometimes they even power down sensitive instruments when passing through that region to avoid glitches or damage.
Wow. So it's a known hazard zone for spacecraft.
Definitely. And the SAA itself isn't staying put either. The data indicates it's actually expanding, it's drifting westwards, and there's even some evidence suggesting it might be splitting into two separate weaker zones.
Splitting. Huh. So understanding that anomaly is pretty critical for anyone operating satellites.
Absolutely vital, especially with more and more satellites going up.
Okay, let me just pause this here for a second. We've talked about weakening, the pole moving, this SAA dent. It sounds kind of dramatic, but the sources were really clear on one point, weren't they?
Yes, absolutely crucial clarification. All these things we're observing, the weakening, the drift, the SAA dynamics, they do not mean a full magnetic pole reversal is about to happen. Not in the next few decades, probably not even in the next few centuries.
Right, so no need to panic about an imminent flip.
No, the field is always in flux. These are just the changes we can measure now with incredible detail. They're part of the field's normal long-term behavior, even if they have shorter-term implications for us.
Okay, good. That's important context. Because the real issue, as the sources frame it, isn't necessarily an imminent flip, but how the field's current state, and space weather in general, affects our technology today.
Precisely. Because our modern world runs on technology that is, frankly, quite sensitive to geomagnetic activity.
And a severely weakened field, whenever that might happen far in the future, would obviously be a huge issue. But even now, with the field basically doing its job, strong solar storms can cause major problems.
Think about satellites. We rely on them for so much.
GPS, obviously.
GPS, global communications, banking transactions rely on timing signals from GPS, weather forecasting, climate monitoring, shipping logistics. I mean, the list is almost endless.
Yeah.
And an intense solar storm can bombard these satellites with radiation and charged particles. This can disrupt their operations, damage components, shorten their lifespan, or, in a worst-case scenario, disable them completely, especially if they pass through a vulnerable area like the SAA during the storm.
Okay, so space assets are at risk. But what about down here on the ground? The sources mentioned power grids too.
Yes, that's a major concern. Terrestrial infrastructure, especially electrical power grids, are vulnerable to something called geomagnetically induced currents, GICs.
GICs. Okay. How does a storm on the sun cause currents in power lines on Earth? That seems like a big jump.
It does, but there's a clear chain of events the sources lay out. It starts with a big eruption on the sun, could be a solar flare, or often a coronal mass ejection, a CME. Huge blob of plasma and magnetic field heading our way.
Right?
When this blast hits Earth's magnetosphere,
Yeah.
it shakes things up. It causes rapid fluctuations in the Earth's magnetic field near the ground.
It makes magnetic field wobble, basically.
That's a good way to put it. And physics tells us that a changing magnetic field induces electrical currents in conductors.
Ah, okay. Like in physics class.
Exactly. And really long conductors, like hundreds of miles of power transmission lines, are very effective at picking up these induced currents. These are the GICs.
The GICs are bad for the grid.
Very bad. Power grids aren't designed to handle these kinds of quasi-DC currents. They can flow into the large transformers at substations, causing them to saturate, overheat, and potentially suffer serious damage or even catastrophic failure.
Failure like burnout,
Yeah.
blackouts.
Yes. A really severe solar storm, something like the Carrington event back in 1859, if it happened today, it could potentially cause cascading transformer failures that could lead to widespread, long-lasting blackouts over huge areas. We're talking potentially weeks or months to replace those giant transformers.
Wow. Okay, that's sobering. So given these risks, what's being done? Who's monitoring this?
There's a pretty significant international effort, actually. The sources highlight several key players.
Okay.
You've got the European Space Agency, ESA. They run the SWARM mission. It's actually a constellation of satellites working together.
Oh, cool.
Yeah, they provide incredibly high-precision measurements of the magnetic field from space, mapping it out in detail and tracking how it changes.
And in the U.S.?
NASA's heavily involved, of course. They study the whole system, the magnetosphere, the geodynamo inside the Earth. The SAA specifically, using data from lots of different missions, they're really digging into the underlying physics.
So ESA and NASA from space. What about ground measurements?
That's where organizations like the U.S. Geological Survey, the USGS, come in. They operate a network of geomagnetic observatories on the ground.
Observatories.
Yeah, fixed locations that constantly measure the magnetic field right here at the surface. This gives that essential ground truth and long-term tracking. They feed into the National Space Weather Program, too.
Okay, so we have space measurements, ground measurements. But what about warnings, like if a big solar storm is coming?
That's the crucial role of NOAA, the National Oceanic and Atmospheric Administration. Specifically, their Space Weather Prediction Center, or SWPC.
SWPC.
Heard of them. They're like the weather service, but for space. They constantly monitor the sun, looking for flares, CMEs, solar wind changes, and they issue alerts and warnings when potentially hazardous space weather is heading our way. It gives grid operators, satellite operators, airlines, and others some lead time to prepare.
It's like an early warning system.
Exactly, a global safety net, trying to connect the dots from the sun to the Earth.
So, looking forward then. We know pole flip isn't like tomorrow's problem. But these solar storms are a current threat. What's the outlook?
The sources really emphasize preparation and resilience, building more robust systems, basically.
They mentioned a kind of SWOT analysis, didn't they?
Yeah.
Strengths, weaknesses.
Yeah, it's a useful way to frame it for our technological infrastructure facing these geomagnetic events. The strengths? Well, our current magnetic field still offers pretty good protection most of the time. And we do have active research and growing awareness. People know this is an issue.
Okay, weaknesses.
Those are pretty clear. Our massive dependence on technology that is vulnerable, the existence of the SAA, the fact the field is weakening, even if slowly, and maybe critically how interconnected everything is. A failure in one part of the grid, for example, can cascade.
Right, domino effect.
Exactly. But then there are opportunities. We can develop more resilient hardware, maybe better shielding for satellites or transformers. We can improve the models that predict solar storms and how the Earth's field itself might evolve, and definitely enhance international cooperation on how to handle these things.
And the threats.
The big one is always the potential for another Carrington-level extreme solar storm. It's low probability in any given year, but the impact would be huge. Then there's the, very long-term possibility of a reversal someday, and maybe the most practical threat right now is just complacency, not preparing adequately for these low-probability, high-impact events.
Yeah, that seems key. The sources really hammered home the need for proactive investment, didn't they?
Absolutely. Investing now in stronger infrastructure, better monitoring, clear mitigation plans, that's how you reduce vulnerability down the road. Whether it's for a major storm next decade or a significantly weaker field centuries from now, it's about prudence.
Okay, so let's try and wrap this up. What are the main takeaways from this deep dive?
Well, first, Earth's magnetic field is definitely dynamic. It's not static, it changes. Second, the changes we see now, the weakening, the pole drift, the SAA, are important scientifically, but they don't signal an imminent pole reversal is just around the corner.
Okay, crucial point.
But third, our deep reliance on technology, especially satellites and power grids, makes us vulnerable right now to space weather events like major solar storms. And we would be even more vulnerable in the distant future if the field weakens substantially.
So the need for continued research, global monitoring, developing ways to mitigate the risks and build resilience. That's not just academic curiosity.
Not at all. The sources frame it as a pragmatic necessity. It's about protecting the fundamental infrastructure of modern life. They even suggest it's creating a whole industry around preparedness and resilience.
An industry of preparedness. Interesting. Okay, so based on all that, here's something maybe for you to think about after listening. We're so deeply plugged into this technological world, power, navigation, communication, everything relies on electricity and satellites. Yet that whole system is fundamentally vulnerable to these massive natural forces from our own planet and our star. How do we really balance the incredible benefits of this advanced world with those underlying vulnerabilities? What does it genuinely mean for us, as a society so dependent on everything working, to be prepared for something that might only happen once a century, or even less often, but could disrupt everything if it does?